Tonight, we're going to confront one of the strangest facts in all of physics. Light behaves like a wave. It creates interference patterns. It diffracts around corners. It does everything a wave should do. But light also behaves like a stream of particles. It strikes detectors one at a time. It delivers energy in discrete packets. It does everything a particle should do. So which is it? Here's the answer most people never hear. It's neither. Light is not a wave pretending to be a particle. It's not a particle pretending to be a wave. It's not switching between two costumes depending on who's watching. Light is something else entirely, something that doesn't exist in our everyday experience, and understanding what that something actually is changes how you see the entire physical universe. Before we go any further, if you find these kinds of deep explorations interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To understand what light really is, you first need to understand what a wave really is. Not in the vague, hand-wavy sense where someone says, "It's like a wave," and moves on. You need to understand what physicists actually mean when they call something a wave, because that definition matters enormously when we get to the part where it stops working. A wave, in classical physics, is a disturbance that travels through a medium. That's the key idea. The medium itself doesn't travel, the disturbance does. Think about dropping a stone into a perfectly calm pond. Ripples spread outward in expanding circles. The pattern moves away from the point of impact, reaching the edges of the pond. But the water itself doesn't flow outward with the ripples. If you placed a small leaf on the surface before the stone hit, the leaf would bob up and down as each ripple passed beneath it, but it would stay roughly in the same spot. The wave carried energy outward from where the stone struck, but the water molecules themselves just moved up and down in place, nudging their neighbors, who nudged their neighbors, passing the disturbance along from molecule to molecule. What traveled across the pond was a pattern, not a substance. Sound works the same way. When someone speaks to you from across a room, their vocal cords vibrate, pushing air molecules back and forth. Those molecules push against their neighbors, which push against their neighbors, creating a chain of compressions and expansions that travels through the air at about 343 meters per second at room temperature. The air molecules themselves don't fly from the speaker's mouth to your ear. They jostle back and forth in place, each one passing the disturbance to the next one in line. What reaches your eardrum is the pattern of pressure changes, not the original air molecules that vibrated near the speaker's lips. You are hearing a traveling pattern. That pattern is the wave. This is what makes a wave in classical physics. It's a traveling disturbance in a medium. The medium stays put. The pattern moves. And that moving pattern carries energy from one place to another without any material thing making the complete journey from source to destination. This idea is fundamental. Keep it in mind, because we're going to come back to it when the story takes its strange turn. Classical waves have specific measurable properties. They have wavelength, the distance between one crest and the next, one complete cycle of the pattern. They have frequency, the number of crests that pass a given point every second. They have amplitude, the height of the crests above the resting position, which determines how much energy the wave carries. A gentle ripple has small amplitude and carries little energy. A tsunami has enormous amplitude and carries devastating energy. Wavelength and frequency are inversely related. The shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. And for any particular type of wave in a given medium, multiplying the wavelength by the frequency gives the wave's speed. These relationships are clean, precise, and universal across every type of classical wave. But there are two particular behaviors that waves exhibit which become crucial for our story. Two things that waves do which particles cannot: interference and diffraction. These are the behaviors that ultimately forced physicists to accept that light is a wave, and they are worth understanding in detail. Interference happens when two waves overlap in the same region of space. Unlike solid objects, which collide and bounce off each other, waves simply pass through one another. When they overlap, they combine. The water surface at any given point rises or falls by the total amount that both waves are pushing it. If two crests arrive at the same point at the same instant, they add together, creating a crest taller than either one alone. This is constructive interference. But if a crest from one wave arrives at the same moment as a trough from another wave of the same size, they cancel each other out. The water stays flat at that point. This is destructive interference. The result is that when waves overlap, they produce patterns of reinforcement and cancellation, alternating regions of strong disturbance and no disturbance at all. No collection of particles could produce this pattern. Two streams of particles hitting the same area just pile up. They don't cancel. Cancellation is a wave phenomenon and a wave phenomenon only. Diffraction is the ability of a wave to bend around obstacles and spread through openings. Stand behind a solid wall while someone plays music on the other side. You can still hear it, even though there is no straight path between you and the speakers. The sound waves don't just travel in a straight line and stop when they hit the wall. They bend around the edges, curling into the region behind the wall, filling the space with sound. The amount of bending depends on how the wavelength compares to the size of the obstacle or opening. When the opening is roughly the same width as the wavelength, diffraction is dramatic. The wave fans out broadly on the other side. When the opening is much larger than the wavelength, the wave passes through mostly in a straight line, with only slight bending at the edges. This is why you can hear someone around a corner but can't see them. Sound waves have wavelengths measured in centimeters to meters, comparable to the size of doorways and walls, so they diffract easily around everyday objects. Visible light has wavelengths measured in hundreds of nanometers, thousands of times smaller than a doorway, so light barely bends around everyday obstacles at all. It appears to travel in rigid, straight lines, but give it an obstacle small enough, close to its wavelength, and light diffracts beautifully. These two behaviors, interference and diffraction, are the signatures of wave behavior. If something shows interference and diffraction, physicists classify it as a wave. If it doesn't, it's probably something else entirely. And for centuries, the question of whether light was a wave or something else was one of the biggest unsettled arguments in all of science. The debate stretches back at least to the 1600s. Isaac Newton, arguably the most influential scientist who ever lived, believed light was made of tiny particles. He called them corpuscles, from the Latin word for small body. Newton had good reasons for this belief. Light travels in straight lines. It casts sharp shadows behind objects. It bounces off polished surfaces the way a ball bounces off a hard floor. These are exactly the behaviors you would expect from a stream of fast-moving, tiny objects. Newton also performed groundbreaking experiments with glass prisms, showing that white light is a mixture of all the colors of the rainbow. He explained this by proposing that different colors corresponded to corpuscles with different properties. Newton's corpuscular theory was detailed, internally consistent, and backed by careful experimentation. But there was a competing idea. At roughly the same time, the Dutch physicist Christiaan Huygens proposed that light was a wave. Huygens showed that many properties of light, including how it reflects off surfaces and how it bends when passing from air into glass or water, could be explained elegantly if light was a disturbance spreading through some kind of invisible medium that filled all of space. He developed a geometric method for predicting how wavefronts propagate, and it worked remarkably well for explaining refraction and reflection. For over a century, the two theories competed. Newton's corpuscular model dominated, partly because Newton's scientific reputation was so towering that few dared challenge him openly, and partly because nobody could demonstrate the single piece of evidence that would prove light was a wave beyond any doubt: interference. If light really was a wave, then two beams of light should be able to cancel each other out under the right conditions. You should be able to add light to light and get darkness. That sounds absurd. How can shining more light on something make it darker? But that is precisely what waves do when they interfere destructively. If you could demonstrate this happening with light, the wave theory would be proven. The problem was that through the entire 1700s, nobody succeeded in making it happen convincingly. Then, in 1803, a British physician and polymath named Thomas Young performed one of the most important experiments in the history of physics. Young's setup was elegant in its simplicity. He allowed sunlight to pass through a single narrow slit to create a coherent source, and then he directed that light onto a barrier containing two narrow slits positioned very close together. Behind the barrier, he placed a screen and observed the pattern the light produced. If light were made of tiny corpuscles, the expected result was straightforward. Particles would pass through one slit or the other, travel in straight lines to the screen, and pile up in two bright bands directly behind the two openings. It would be like spraying paint through two holes in a stencil. You would get two stripes of paint on the wall behind, nothing more. But that is not what Young saw. Instead of two bright bands, the screen displayed a series of alternating bright and dark stripes spread across its surface. Bright, dark, bright, dark, bright, repeating in a regular pattern far wider than the two slits alone could account for. This was an interference pattern. The bright stripes appeared at locations where light waves from the two slits arrived perfectly in step, crest meeting crest, reinforcing each other through constructive interference. The dark stripes appeared at locations where light from one slit arrived exactly half a wavelength out of step with light from the other slit, crest meeting trough, cancelling through destructive interference. Young had added light to light and produced darkness. That is something only waves can do. If you throw two handfuls of sand at the same spot on a floor, you get a bigger pile. The sand doesn't cancel itself out and leave a bare patch, but waves can cancel. And light was cancelling in exactly the way wave theory predicted. The pattern was unmistakable. Young's experiment did more than simply prove light behaves as a wave. It allowed him to measure light's wavelength for the first time. By analysing the spacing between the bright and dark bands, and knowing the distance between the two slits and the distance to the screen, Young calculated that visible light has wavelengths between roughly 400 and 700 nanometers. Red light has the longer wavelengths near the 700 nanometer end of that range. Violet light has the shorter wavelengths near 400 nanometers. Every color of the rainbow corresponds to a specific wavelength in between. These numbers are extraordinarily small. A nanometer is 1/1000th of a meter. You could fit over 100 wavelengths of red light across the thickness of a single sheet of paper. And this explains why Newton's particle theory had seemed so convincing for so long. Light's wavelengths are thousands of times smaller than the objects we encounter in everyday life. When a wave meets obstacles much larger than its wavelength, it travels in nearly straight lines and casts sharp shadows, mimicking the behavior of particles. Only when light encounters features comparable in size to its wavelength does wave behavior become dramatically visible. Newton was not wrong about what he observed. Light genuinely does travel in straight lines and cast crisp shadows in normal circumstances. He simply didn't have the tools to reveal what happens when you zoom in to the scale of light's actual wavelength. Diffraction experiments provided further confirmation. When light passes through a very narrow slit, it does not simply create a tiny bright spot on the far side. It fans outward, spreading into a broad pattern of bright and dim regions. This is exactly what wave theory predicts. Augustin-Jean Fresnel developed a rigorous mathematical theory of diffraction in the early 1800s, showing precisely how light waves interfere after passing through openings and around obstacles. His calculations matched experimental observations with stunning accuracy. One of the most dramatic moments in this story came from a prediction that was meant to disprove Fresnel's theory, but ended up confirming it spectacularly. When Fresnel presented his wave theory of light to the French Academy of Sciences in 1818, the mathematician Simeon Denis Poisson examined the equations and pointed out what he considered a fatal flaw. The theory predicted that if you shone light onto a small circular disk, there should be a bright spot at the very center of the shadow behind the disk. This seemed ridiculous. A shadow is dark. That is what a shadow means. A bright spot at the center of a shadow was obviously wrong, so the theory must be wrong. But another scientist, Dominique François Arago, decided to actually perform the experiment rather than just argue about it. And when he did, the bright spot was there, right at the center of the shadow, exactly where Fresnel's equations predicted. Light waves bending around the edges of the disk converged at the center, interfering constructively to produce a point of brightness. The theory's most absurd-seeming prediction turned out to be its most stunning triumph. The spot is now called the Arago spot, or the Poisson spot, depending on whether you want to credit the person who confirmed it or the person who accidentally predicted it while trying to prove it impossible. By the middle of the 1800s, the wave theory of light had won the debate. Interference and diffraction had been demonstrated beyond any reasonable doubt. The mathematical framework explained observations with extraordinary precision. But one profound question remained. If light is a wave, what is it a wave of? Sound waves are disturbances in air. Water waves are disturbances in water. Waves in a guitar string are disturbances in the metal or nylon of the string. Every wave anyone had ever encountered was a disturbance in some physical medium. So what medium was light rippling through? Light travels across the vacuum of space, from the sun to the earth, through regions where there is no air, no water, no material substance of any kind. What was doing the waving? This is where James Clerk Maxwell changed everything. In the 1860s, Maxwell was working to unify the theories of electricity and magnetism, two phenomena that experiments had revealed were deeply connected. Scientists already knew that electric charges produce electric fields radiating outward from the charge. They knew that moving electric charges produce magnetic fields circling around them. Michael Faraday had demonstrated that a changing magnetic field produces an electric field, which is the principle behind every electric generator on the planet. And experiments showed that a changing electric field produces a magnetic field. There was a deep, reciprocal relationship between electricity and magnetism, but no one had woven all of these observations into a single, coherent mathematical framework. Maxwell did exactly that. He wrote down a set of 4 equations that captured all known electrical and magnetic phenomena in one unified system. These are now called Maxwell's equations, and they stand among the most important equations in the history of science. But when Maxwell studied his own equations carefully, pushing the mathematics to see what it implied, he discovered something nobody expected. The equations predicted that oscillating electric and magnetic fields could sustain each other, leapfrogging through space in a self-propagating wave. A changing electric field would generate a changing magnetic field, which would generate another changing electric field, which would generate another changing magnetic field, on and on, the whole disturbance racing forward through empty space. No medium was required. The electric and magnetic fields were the medium, or rather, the electromagnetic field itself was the thing doing the waving. Maxwell then calculated the speed these electromagnetic waves should travel at. The speed was determined entirely by two constants that had already been measured in electrical and magnetic experiments: the electric permittivity and the magnetic permeability of free space. When he plugged in the known values, the result came out to approximately 300,000 kilometers per second. Maxwell immediately recognized that number. It was the measured speed of light. The agreement was far too precise to be coincidence. Maxwell declared that light itself is an electromagnetic wave. It is a self-sustaining oscillation of electric and magnetic fields, propagating through the vacuum at a speed set by the fundamental properties of electromagnetism. This was one of the great unifications in the history of human thought. Electricity, magnetism, and light, three categories of phenomena that had seemed entirely separate, turned out to be different aspects of the same underlying reality. Light is an electromagnetic wave. And it isn't just visible light. Maxwell's equations predicted the existence of electromagnetic waves at all wavelengths and frequencies. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, all are electromagnetic waves. They differ only in wavelength and frequency. Radio waves have wavelengths measured in meters or even kilometers. Visible light has wavelengths in hundreds of nanometers. Gamma rays have wavelengths smaller than atomic nuclei. But every single one is the same fundamental phenomenon: oscillating electric and magnetic fields traveling through space at the speed of light. In 1887, the German physicist Heinrich Hertz confirmed Maxwell's predictions experimentally. Hertz built a device that generated electromagnetic waves with wavelengths of several meters, far longer than anything the eye can see, what we would now call radio waves. He demonstrated that these waves traveled at the speed of light, could be reflected off metal surfaces, refracted when passing through certain materials, focused by curved reflectors, and polarized by wire grids. They behaved in every measurable way like light, just at a different wavelength. Maxwell's theory was not just elegant mathematics. It described physical reality. And Hertz's confirmation was just the beginning. Once physicists understood that electromagnetic waves could exist at any wavelength, they realized that visible light was only a tiny sliver of something much larger. The human eye responds to wavelengths between roughly 400 and 700 nanometers. That is an incredibly narrow band. Below 400 nanometers lies ultraviolet radiation, invisible to our eyes but capable of causing sunburn and driving chemical reactions. Below that are X-rays, with wavelengths comparable to the size of atoms, capable of passing through flesh and revealing bones. Shorter still are gamma rays, with wavelengths smaller than atomic nuclei, produced in nuclear reactions and the most energetic events in the universe. On the other side of visible light lie longer wavelengths, infrared radiation, felt as warmth radiating from a fire but invisible to the eye. Microwaves, which would eventually be used to heat food and transmit signals, and radio waves, with wavelengths stretching from centimeters to kilometers, which would soon carry voices and music across continents and oceans. All of these were the same phenomenon. All of them were oscillations of the electromagnetic field, differing only in wavelength and frequency. The eye had been showing us a keyhole view of a vast spectrum, and Maxwell's theory threw the door wide open. Throughout the final decades of the 1800s, each new region of the spectrum was explored and confirmed. Wilhelm Röntgen discovered X-rays in 1895, a mysterious new form of radiation that could pass through flesh and expose photographic plates. Their electromagnetic nature was confirmed over the following 2 decades, and they too fit perfectly within Maxwell's framework. Engineers began building devices to generate and detect radio waves, laying the groundwork for a communications revolution that would transform civilization. Every new discovery fit perfectly within Maxwell's framework. The equations never failed. They predicted the speed of every electromagnetic wave, the way it would reflect and refract, how it would interact with matter, and observation after observation matched the predictions with extraordinary precision. The sense of accomplishment in the physics community was immense. For the first time in history, scientists understood what light actually is, not just how it behaves, but what it fundamentally is at the physical level. It is an electromagnetic wave, a ripple in the electromagnetic field, carrying energy through space at a speed determined by the fundamental constants of electricity and magnetism. This was not a guess or a tentative hypothesis. It was confirmed by decades of experiments, backed by a mathematical framework of remarkable elegance and power, and consistent with every observation ever made. Some physicists at the time felt that the major work of physics was essentially complete. The universe seemed to operate according to well-understood laws. Newton's mechanics described the motion of objects from planets to billiard balls. Maxwell's electromagnetism described light, electricity, and magnetism. Thermodynamics and statistical mechanics described heat and energy. There were a few loose ends, some puzzling experimental results that didn't quite fit, but these were widely seen as minor problems that would be tidied up with better measurements or slightly refined calculations. The fundamental framework seemed secure. Lord Kelvin reportedly remarked that physics was essentially finished, with only two small clouds on the horizon. One of those clouds was the failure to detect the luminiferous ether, the hypothetical medium through which light waves were supposed to travel, a puzzle that Einstein would resolve with special relativity. The other was the problem of black body radiation, the question of how hot objects glow. That second cloud was about to produce a thunderstorm that would reshape all of physics. Nobody saw it coming. The wave theory of light had been so thoroughly validated by so many independent experiments across so many different phenomena that questioning it seemed almost absurd. If you had asked a physicist in 1895 whether light was a wave, the answer would have been immediate and confident. Of course it is a wave. We have proven it beyond any doubt. We know what kind of wave it is. We know the equations it obeys. We know its speed, its spectrum, its behavior in every situation we have tested. Light is an electromagnetic wave. Case closed. And this is precisely why what happened next was so shocking. The problem didn't come from some exotic corner of physics. It came from something utterly mundane. A hot oven. And then the whole picture started to crack. The first fracture came from an unexpected problem. Physicists were trying to understand something that seemed simple enough. How does a hot object glow? When you heat a piece of metal in a forge, it first glows dull red, then brighter orange, then yellow, then white as the temperature climbs. This is thermal radiation, electromagnetic waves emitted by matter because of its temperature. Every object above absolute zero emits some thermal radiation. The hotter the object, the more radiation it emits, and the shorter the peak wavelength becomes. A warm human body emits infrared radiation you can't see. A red-hot piece of iron emits visible light. The surface of the Sun, at about 5,500 degrees Celsius, emits strongly across the visible spectrum, which is why sunlight appears white. Physicists wanted to predict exactly how much energy a hot object radiates at each wavelength. To make the problem precise, they considered an idealized object called a blackbody, a perfect absorber that soaks up all radiation hitting it and emits radiation based purely on its temperature. A small hole in the wall of a uniformly heated oven is an excellent approximation of a blackbody. Radiation enters the hole, bounces around inside the cavity, reaching thermal equilibrium with the walls, and the radiation escaping through the hole has a spectrum determined entirely by the temperature. Using classical physics, Maxwell's electromagnetic wave theory, and the statistical mechanics developed by Ludwig Boltzmann, physicists attempted to calculate the blackbody spectrum, the precise distribution of energy across all wavelengths. Lord Rayleigh and James Jeans carried out the calculation rigorously. The result was a disaster. At long wavelengths, the formula worked beautifully. It matched experimental measurements. But at short wavelengths, in the ultraviolet region and beyond, the formula predicted that the energy emitted should rise without limit. As wavelength decreased, the predicted energy climbed higher and higher, soaring toward infinity. This meant that any warm object should radiate infinite energy, concentrated overwhelmingly in the ultraviolet and shorter wavelengths. A heated oven, according to the best physics of the day, should be flooding the room with lethal doses of ultraviolet light, X-rays, and gamma rays. Obviously, this does not happen. You can stand in front of an open oven and feel warmth on your face, not a death ray. The prediction was not slightly off. It was infinitely wrong. Physicists called this the ultraviolet catastrophe, and the name was deserved. It was not a small discrepancy to be smoothed over with a better approximation. It was a fundamental breakdown of the theory at short wavelengths, a sign that something deep in the physics was missing. What made the ultraviolet catastrophe so disturbing was that every step of the calculation used well-tested, trusted physics. Maxwell's equations for the electromagnetic field were confirmed by experiment. Boltzmann's statistical mechanics worked beautifully for gases, for heat engines, for countless other systems. Yet when combined to describe the simplest possible radiation problem, they produced nonsense. Something foundational was wrong, not with the experiments, but with the theoretical framework itself. In the year 1900, the German physicist Max Planck found a way out. But the price was an assumption that seemed almost heretical at the time. Planck proposed that the energy exchanged between the walls of the cavity and the electromagnetic radiation could not take on just any value continuously. Instead, energy could only be emitted or absorbed in discrete, indivisible packets. Each packet carried an amount of energy equal to the frequency of the radiation multiplied by a new fundamental constant, a tiny number that Planck introduced into physics for the first time. This constant, now called Planck's constant, is extraordinarily small, roughly 6.63 times 10 to the negative 34 joule seconds. But its consequences are enormous. Here is why Planck's assumption fixed the problem. In the classical picture, the electromagnetic field inside the cavity has modes of vibration at every frequency, including extremely high frequencies. Classical physics says every mode should carry the same average energy, regardless of frequency. This is what drives the ultraviolet catastrophe. There are infinitely many high-frequency modes, each carrying the same energy, producing infinite total radiation. But with Planck's quantization rule, the energy required to excite a single quantum of a high-frequency mode is very large, because each quantum's energy equals the frequency times Planck's constant. At the temperatures of ordinary hot objects, there simply is not enough thermal energy available to populate those high-frequency modes. You cannot put half a quantum of energy into a mode. It is all or nothing. Either the mode has at least one full quantum of energy, or it has none. And for high-frequency modes, the energy of even a single quantum is so large that the mode almost never gets excited. This naturally and elegantly suppresses the short wavelength radiation, exactly fixing the ultraviolet catastrophe. The predicted spectrum, calculated with Planck's quantization assumption, matched the experimentally observed blackbody spectrum with perfect precision across every wavelength, from the longest infrared to the shortest ultraviolet. But think carefully about what Planck had done. He had introduced a fundamental granularity into the exchange of energy between matter and the electromagnetic field. In the classical wave picture, energy is smooth and continuous. You can make a wave carry any amount of energy you wish. There is no minimum portion. You can dim a wave smoothly all the way down towards zero, passing through every possible intensity along the way. But Planck was saying that energy exchange between matter and light comes in lumps. You can emit 1 lump, or 2 lumps, or 17 lumps, but you cannot emit half a lump or 3/4 of a lump. The exchange is quantized, meaning it comes in discrete, indivisible units. Planck himself was deeply uncomfortable with this idea. He saw it initially as a mathematical trick, a clever assumption that happened to make the calculation produce the right answer without necessarily reflecting how nature actually works. He spent years after his breakthrough trying to derive the same result using purely classical reasoning, hoping to show that the quantization was just a mathematical convenience that could be explained away within the existing framework. He never succeeded. The quantization was not a trick. It was a clue, pointing toward a revolution in physics that Planck himself did not fully anticipate and was not entirely comfortable with. He had opened a door and wasn't sure he wanted to walk through it. The classical wave theory of light, the magnificent framework built over a century by Young, Fresnel, Maxwell and Hertz, had developed an undeniable crack. The wave picture explained interference beautifully. It explained diffraction. It explained polarization, reflection, refraction, the entire electromagnetic spectrum. It even told you what light fundamentally is: oscillating electric and magnetic fields that sustain each other as they race through space. But it could not explain how light exchanges energy with matter at the most basic level. It predicted that any hot object should radiate infinite energy, which is physically absurd. Classical waves were not the complete story. And the implications of Planck's fix were about to become far more radical than even he imagined. Because if the energy exchanged between light and matter comes in discrete, indivisible packets, if there are minimum portions of electromagnetic energy at every frequency, then perhaps light itself carries energy in discrete portions. Perhaps the smooth, continuous electromagnetic wave is not the deepest description of what light is. Perhaps, in spite of all the overwhelming evidence for wave behavior, there is something undeniably, irreducibly particle-like about light after all. The wave theory was not wrong. Interference is real. Diffraction is real. Maxwell's equations are correct. But the wave theory was incomplete. It captured one face of light's nature beautifully, while completely missing another. And that missing face was about to turn physics inside out. The wave theory explained light beautifully. Interference, diffraction, polarization, the entire electromagnetic spectrum, all of it worked perfectly within Maxwell's framework. But Planck's discovery had pulled at a loose thread, and in 1905, a young patent clerk in Bern, Switzerland, pulled that thread so hard, the entire fabric started to unravel. Albert Einstein was 26 years old when he published 4 papers in a single year, each one transformative enough to define any physicist's entire career. One introduced special relativity. Another explained Brownian motion, providing powerful evidence that atoms are real. But the paper that would eventually earn Einstein the Nobel Prize in 1921 was not about relativity or atoms. It was about something that seemed much simpler. It was about light shining on metal. The phenomenon was called the photoelectric effect, and it had been noticed accidentally by Heinrich Hertz in 1887, the same year Hertz confirmed Maxwell's prediction of electromagnetic waves. While generating electromagnetic sparks in his laboratory, Hertz observed that ultraviolet light falling on the spark gap made it easier for sparks to jump across. Something about the ultraviolet light was helping electrical charges move. Later experiments by Philip Leonard and others pinned down exactly what was happening. When light of sufficiently high frequency strikes a metal surface, electrons are knocked loose from the metal and ejected into the surrounding space. You can detect those electrons, measure their energy, count them. Light was literally kicking particles out of solid matter. This was interesting, but not immediately alarming. After all, waves carry energy, and if enough energy arrives at the surface, it makes sense that electrons could absorb that energy and break free. Classical wave theory had a straightforward prediction for how this should work. In the wave picture, the energy of light depends on its intensity, which is related to the wave's amplitude. Brighter light means bigger waves, which means more energy delivered to the surface every second. So the classical expectation went like this: shine brighter light on the metal, and the ejected electrons should fly off faster, because they've absorbed more energy from the more powerful wave. And if you dim the light enough, using a very feeble source, you might need to wait a while for enough energy to slowly accumulate at a single electron's location before that electron has absorbed enough to break free. But eventually, with enough patience, even very dim light of any color should liberate electrons. The frequency of the light shouldn't matter much. What matters is the total energy arriving at the surface, which is determined by brightness. Every single one of those predictions turned out to be wrong. Here is what actually happens. If you shine red light on certain metals, no electrons come out. It doesn't matter how blindingly bright you make the red light. You can flood the surface with the most intense red light you can produce, and not a single electron budges. Zero. Nothing. No matter how long you wait. The energy is arriving continuously in enormous quantities according to the wave picture, plenty of it, but no electrons are liberated. The surface just sits there, completely unaffected. Now switch to blue light or ultraviolet light. Even extremely dim ultraviolet light, so faint you can barely detect it with instruments, instantly produces electrons the moment it touches the metal. There is no delay, no waiting for energy to accumulate. The ejection is immediate. One photon arrives, one electron leaves. And here is the detail that truly baffled classical physics. Making the ultraviolet light brighter does not make the individual electrons come off faster. It produces more electrons, yes, but each electron carries the same maximum energy, regardless of whether the light source is dim or blazing. What does change the electron's energy is the frequency of the light. Higher frequency light produces faster electrons. Lower frequency light produces slower electrons. And below a certain threshold frequency specific to each type of metal, no electrons are produced at all, no matter how intense the light is. This pattern made absolutely no sense within the classical wave framework. In the wave picture, energy depends on amplitude, on brightness. Frequency determines only the color of the light, not how much energy it delivers. A dim blue wave carries less total energy per second than a bright red wave. So why would dim blue light kick electrons loose, while bright red light cannot? Why would the speed of the ejected electrons depend on frequency rather than intensity? Why is there a sharp threshold frequency below which nothing happens, regardless of how much power you pour in? The wave theory had no answers. It was not that the theory gave the wrong numbers, it predicted the wrong relationships entirely. Einstein's explanation was radical. He proposed that light itself comes in discrete, indivisible packets of energy. Not just that the energy exchange between light and matter is quantized, which is roughly what Planck had cautiously suggested, but that the light beam itself is made of individual energy bundles traveling through space. Einstein called them light quanta. Each quantum carries a specific amount of energy, determined entirely by the frequency of the light. The energy of a single quantum equals Planck's constant multiplied by the frequency. Higher frequency means each quantum carries more energy. Lower frequency means each quantum carries less. This has nothing to do with how bright the light is. Brightness determines how many quanta are in the beam, not how much energy each individual quantum carries. A bright beam contains many quanta. A dim beam contains few. But every single quantum in a beam of a given frequency carries exactly the same energy. no more and no less. Now, the photoelectric effect makes perfect sense. When light hits a metal surface, each individual quantum interacts with a single electron in a private one-on-one encounter. The electron either absorbs the quantum's full energy or it doesn't. There is no partial absorption. It is all or nothing. If the quantum's energy exceeds the minimum energy needed to free the electron from the metal, a quantity called the work function, the electron is ejected. Whatever energy remains after paying the work function becomes the electron's kinetic energy, the energy of its motion as it flies away from the surface. If the quantum's energy falls below the work function, the electron cannot escape, no matter how many low-energy quanta hit the surface. 1,000 quanta that are each individually too weak cannot pool their energy together to free a single electron. Each quantum acts alone. Each interaction is independent. This explains everything. Below the threshold frequency, each quantum lacks the minimum energy needed to free an electron. Increasing the brightness just sends more weak quanta, every one of which individually fails. It is like trying to knock down a reinforced door by throwing hundreds of cotton balls at it. Each cotton ball is too weak, no matter how many you throw. Above the threshold frequency, even a single quantum has enough energy to liberate an electron, which is why even extremely dim light produces electrons with no delay. The electron doesn't need to accumulate energy over time from a slow building wave. One quantum is sufficient. It arrives, it delivers its energy, the electron is free. And the speed of the ejected electrons depends on frequency, because higher frequency quanta carry more energy, leaving more excess after the work function has been paid. Einstein's light quantum hypothesis was not immediately accepted. It was too radical. Planck himself opposed it for years. The experimental physicist Robert Millikan spent roughly a decade performing meticulous experiments specifically designed to disprove Einstein's theory. Millikan varied the frequency and intensity of the light systematically, measured the energy of the ejected electrons with extreme precision, tested multiple metals with different work functions, and checked every prediction Einstein's equation made. After years of painstaking work, Millikan's conclusion was reluctant but unambiguous. Every prediction of Einstein's equation was confirmed with impressive accuracy. The relationship between photon energy, frequency, and the kinetic energy of ejected electrons held perfectly across every material and every frequency tested. Millikan won his own Nobel Prize in part for these measurements, even though the very results he obtained flatly contradicted the conclusion he had set out to demonstrate. But the photoelectric effect was only the first blow. In 1923, a second experiment delivered evidence so direct and so visceral that it essentially ended the debate over whether light carries energy in discrete bundles. The American physicist Arthur Holly Compton was studying what happens when X-rays scatter off electrons. X-rays are electromagnetic waves with very short wavelengths and very high frequencies, far beyond the range of visible light. When Compton directed a beam of X-rays at a target containing loosely bound electrons, the X-rays scattered off those electrons and emerged at various angles. Classical wave theory had a clear prediction. The scattered X-rays should have the same wavelength as the incoming beam. A wave bouncing off a charged particle might be redirected, but it should oscillate at the same frequency and maintain the same wavelength. That is what classical electromagnetic waves do when they scatter off charges. But Compton found that the scattered X-rays had longer wavelengths than the originals. The wavelength increased, which means the frequency decreased, which means the energy decreased. The X-rays were losing energy in the scattering process. Moreover, the amount of wavelength increase depended precisely on the angle at which the X-rays scattered. X-rays deflected at large angles showed a bigger wavelength increase than those deflected at small angles. X-rays that bounced nearly straight backward showed the greatest shift. Those that barely glanced to the side showed the smallest. This pattern was utterly inexplicable in the classical wave picture, but it was exactly what you would expect if the X-rays were behaving like individual projectiles colliding with electrons. Picture two billiard balls on a table. The cue ball strikes the target ball. After the collision, the cue ball moves more slowly because it transferred some of its kinetic energy and momentum to the target ball. How much energy and momentum it loses depends on the geometry of the collision. A head-on hit transfers the most. A glancing blow transfers the least. Compton showed that his X-ray scattering data matched precisely this kind of particle collision physics. He applied the conservation of energy and the conservation of momentum, the same laws governing any two-body collision, and the predicted wavelength shifts at every scattering angle matched his measurements exactly. Each X-ray quantum was behaving like an individual object, colliding with an individual electron, transferring both energy and momentum in a single discrete interaction, and bouncing away with less energy than it started with. This was profound evidence because it demonstrated something the photoelectric effect alone could not. The photoelectric effect showed that light delivers energy in discrete lumps. The Compton effect showed that light also carries momentum in discrete lumps. Each quantum of light physically shoves things. It hits an electron the way one object hits another, exchanging both energy and momentum according to the same conservation laws that govern collisions between baseballs, between atoms, between any two objects in the physical world. The quantum of light even changes its own properties after the collision, losing energy and gaining wavelength, exactly as a ball slows down after striking another ball. Light was not just depositing energy, it was engaging in mechanical collisions. After Compton's result, resistance crumbled. The photoelectric effect had been radical enough, but you could still argue about interpretations, still hope the quantization was somehow a property of the metal rather than the light. The Compton effect left no room for that. The X-ray quanta were carrying momentum, exchanging it in collisions and recoiling with altered wavelengths. This was not an ambiguity in how matter absorbs energy. This was light itself behaving as a collection of individual objects. Physicists began calling light quanta by a new name. In 1926, the physical chemist Gilbert Lewis coined the word photon. The name stuck, and it has been used ever since. A photon is a quantum of electromagnetic radiation, an indivisible packet of energy and momentum. As detection technology improved through the 20th century, the particle-like nature of light became even more dramatic and more personal. Modern photodetectors, devices designed to register light at the lowest possible intensities, detect individual photons one at a time. A photomultiplier tube takes a single photon, uses it to knock loose a single electron from a specially coated surface, and then amplifies that one electron through a cascade of collisions until it becomes a measurable electrical pulse. One photon in, one pulse out. Each pulse represents one quantum of light arriving at the detector. You can connect the detector to a speaker and listen. In a dark laboratory, the device produces distinct clicks. Plick, plick, plick. Not a continuous hiss. Not a smooth wash of noise rising and falling with intensity. Individual, discrete, separated clicks, each one marking the arrival of a single photon. If you reduce the intensity of a light source to extraordinary faintness, filtering it down until the beam is so weak that only a handful of photons arrive each second, the clicks become sparse, but they never become fractional. You hear click, silence, Click. Long silence. Click. Each click is one photon. There is never half a click. There is never 70% of a click. Detection events are binary. Either a whole photon arrived or nothing did. The light comes in complete, indivisible units. This behavior extends to imaging. If you set up a camera capable of recording individual photons and expose it to extremely dim light, the image doesn't appear as a uniformly faint version of what you'd see with brighter illumination. Instead, individual dots appear on the sensor, one at a time, scattered in seemingly random positions. Each dot represents one photon arriving at one location. With very few photons, the image looks like static, a seemingly random sprinkle of isolated dots with no discernible pattern. But as more photons accumulate over time, thousands, then tens of thousands, then millions, the dots begin to cluster. Bright regions collect more dots, dark regions collect fewer. A recognizable image gradually emerges, built point by point from individual detection events. The final image was always there as a statistical tendency encoded in the probabilities, but it assembled itself one photon at a time, one discrete event after another. So by the early 20th century, physicists faced two overwhelming and apparently contradictory bodies of evidence. On one side, interference and diffraction proved beyond any reasonable doubt that light behaves as a wave. Waves can cancel, particles cannot. Light cancels. Therefore, light must be a wave. On the other side, the photoelectric effect, the Compton effect, and single photon detection proved beyond any reasonable doubt that light behaves as a stream of particles. Energy and momentum are delivered in discrete, indivisible bundles. Detection events are individual and localized. Therefore, light must be a particle. Both arguments are airtight based on their evidence, and both cannot be simultaneously true in any classical sense. A classical wave is smooth, continuous, spread out across space, carrying energy proportional to its amplitude. A classical particle is a compact, localized, discrete object with a definite position and a definite trajectory at every moment. These are contradictory descriptions. Something cannot be both spread out and localized. Something cannot be both continuous and discrete. Yet light seemed to be both. But here is what you need to understand very clearly before we go any further. The answer is not that light is literally a classical particle. The photon is not a tiny solid pellet. It is not a miniature bullet flying through space along a precise, straight-line path. Calling a photon a particle is just as misleading as calling it a wave, because everything we normally mean by the word particle fails when applied to photons. Consider what a classical particle actually is. You can picture a marble rolling across a table. It has a definite position at every moment. You can point to it and say it is right there. It has a definite trajectory. You can track its path as it rolls from one edge of the table to the other. It has a definite speed and direction at every instant. If you know where it is now and how fast it's moving, you can predict exactly where it will be 1 second from now, 10 seconds from now, an hour from now. These properties, definite position, definite trajectory, definite momentum at every instant, are what make something a particle in the classical sense. Photons have none of these properties between the moment they are emitted and the moment they are detected. You cannot track a photon's path through space. You know where it was created and you know where it was absorbed, but you cannot say what route it took between those two events. This is not a limitation of our instruments. It is not that we lack a sufficiently clever camera to photograph the photon mid-flight. The photon genuinely does not possess a definite trajectory between emission and detection. Asking what path a photon took is like asking what color the number 7 is. The question assumes a property that the thing simply doesn't have. This becomes starkly visible in experiments with single photons and beam splitters. A beam splitter is a partially reflective mirror. When a single photon hits a beam splitter, classical intuition says the photon should either reflect or pass through. It is an indivisible quantum after all. It can't split in half. And indeed, if you place a detector on each output path, you never detect half a photon on both sides simultaneously. Every detection event registers one whole photon in one detector only, never two half photons in both detectors at once. But here is the strange part. If instead of placing detectors immediately after the beam splitter, you recombine the two paths using mirrors and let them overlap, you observe an interference pattern. The photon appears to have traveled both paths simultaneously, interfering with itself, producing constructive or destructive interference depending on the difference in path lengths. A single, indivisible photon interfering with itself. But if you add a detector to determine which path the photon actually took, the interference pattern vanishes. A classical particle cannot do this. A marble rolling toward a fork in a road takes one path or the other. It doesn't take both paths and interfere with itself at the junction where they meet. That is wave behavior. Yet when you check which path the photon actually traveled, you always find it on one path and one path only. That is particle behavior. The photon exhibits wave properties when you don't measure its route and particle properties when you do. It is not switching between two modes depending on whether you're looking. It is something that simply doesn't fit into either classical category. Let's sit with this strangeness for a moment, because it is worth feeling the full weight of what these experiments reveal. The beam splitter result is not some minor technical curiosity buried in a physics journal. It strikes directly at our most basic assumptions about physical objects and how they move through the world. Think about what you take for granted every time you watch anything move. A car approaches an intersection and turns left. A ball rolls toward a gap in a fence and passes through it. A raindrop falls and lands in one spot, not two. Every object you have ever watched in your life existed in one definite place at each moment and followed one definite path from origin to destination. You don't think about this consciously because nothing in everyday experience has ever violated it. It is so deeply woven into how your brain models the world that it doesn't feel like an assumption at all. It feels like logic. And yet this assumption, this bedrock conviction that things travel along single, definite routes, fails completely for photons. When a single photon encounters a beam splitter and the two output paths are recombined with mirrors, the photon interferes with itself. The result depends on the precise difference in path lengths, down to fractions of a wavelength. If one path is slightly longer than the other, the interference changes. Adjust the path length by half a wavelength, and a photon that was almost certain to emerge from one output is now almost certain to emerge from the other. The photon is sensitive to what is happening on both paths, even though it is a single, indivisible quantum. If you block one path entirely, the interference vanishes. Both paths must be available for the interference to occur. Yet if you check which path the photon actually took, you find it on one path only, and the interference disappears. This means the photon does not take a path in any classical sense. Between emission and detection, it does not have a location. It is not at point A, then at point B, then at point C along some trajectory. This is not because we are ignorant of the photon's position. It is because the photon genuinely does not possess a position during that interval. Position is a property that becomes defined at the moment of detection, not before. Before detection, asking where the photon is resembles asking what a book weighs while it is still being written. The question assumes a definite answer exists, and it does not. This has been tested with exquisite precision. Physicists have performed experiments where a single photon is sent into an interferometer and the two paths are separated by meters, sometimes by kilometers using fiber optic cables. Even when the paths are separated by distances you could walk across in minutes, the single photon shows interference effects sensitive to both paths. Whatever the photon is doing between emission and detection, it is not traveling along a single definite route through space. The concept of trajectory, so fundamental to what we mean by a particle, simply does not apply. And the strangeness deepens when you consider what it means for the photon to have no rest state. A marble can sit motionless on a table. You can walk around it, examine it from every angle, measure its size and weight at your leisure. It persists. It waits for you. It has an existence that is independent of your interaction with it. A photon cannot do any of this. A photon exists only in transit. It is created in one interaction and destroyed in another, and between those two events, it moves at exactly the speed of light. You cannot slow it down to study it. You cannot trap it in a box and examine it the way you would examine a rock or a coin. The only way to detect a photon is to absorb it, which destroys it. Every observation of a photon is a record of its death. You never see a photon. You see the aftermath of a photon being absorbed by the detector. The photon itself is gone. This is fundamentally different from any object in ordinary experience. Every physical thing you have ever held, watched, or touched was something that persisted while you observed it. The observation didn't destroy the object. You could look at a chair and it would still be there afterward. But a photon is consumed by the act of observation. You cannot observe it and preserve it. Detection and destruction are the same event. A photon is not a thing that exists in the way everyday objects exist. It is an event, a transaction between a source and a detector, with something profoundly strange happening in between. Furthermore, a photon's energy is determined by its frequency. The energy of a single photon equals Planck's constant times the frequency. But frequency is fundamentally a wave concept. Particles don't have frequencies. A marble rolling across a table doesn't oscillate. It doesn't have a wavelength or a period. Yet the photon's most particle-like property, the discrete bundle of energy it carries, is calculated directly from its most wave-like property, its frequency. The two natures aren't separate alternatives you can choose between. They are tangled together at the deepest level, interlocked in a way that classical physics has no framework to explain. A photon also has no rest mass. Every material particle you've ever encountered has mass. Marbles, bullets, grains of sand, atoms, electrons, all of them have mass. They can sit still, they can move slowly or quickly. You can speed them up or slow them down by applying forces. A photon can do none of this. A photon always travels at exactly the speed of light, roughly 300,000 kilometers per second. It cannot slow down. It cannot speed up. It cannot be brought to rest. From the instant it is created to the instant it is absorbed, it moves at light speed. There is no reference frame in which a photon is stationary. There is no laboratory anywhere in the universe where a photon sits on a table waiting for you to examine it. This is nothing like the behavior of a marble, or a bullet, or any other object we would normally call a particle. And perhaps most strikingly of all, consider what happens when you send individual photons, one at a time, through the very same double-slit arrangement that Thomas Young used over 2 centuries ago to prove light is a wave. You set up 2 narrow slits and a detector screen behind them. You reduce the intensity of your light source until only 1 photon is in the apparatus at any given moment. There is never more than a single photon between the source and the screen. Classical particle logic says each photon should pass through one slit or the other and hit the screen somewhere behind that slit. Over time, as photon after photon arrives, you should see 2 piles of detections accumulating behind the 2 openings, just as you'd expect from tossing tiny pebbles, one at a time, through 2 holes in a fence. But that is not what happens. Each individual photon does land at a single specific point on the detector, registering as one distinct dot. That part looks particle-like. But after thousands and then millions of photons have arrived, each one alone, never more than one present in the apparatus at any instant, the accumulated pattern of dots forms the unmistakable signature of wave interference. Alternating bands of many detections and virtually no detections stretch across the screen, exactly matching the interference pattern Young observed with bright, continuous light. The individual photons, arriving one at a time with nothing to interfere with, somehow collectively build up a pattern that only waves can produce. This is not the behavior of a classical particle. Classical particles do not interfere with themselves. If you fire bullets one at a time through two holes in a wall, you get two clusters of bullet holes behind the two openings. You never get alternating stripes of bullet holes and bare patches. That simply doesn't happen in the everyday world. And it is not the behavior of a classical wave either. A classical wave passes through both slits and interferes with itself smoothly, arriving at the screen as a continuous pattern of varying intensity, not as individual dots appearing one at a time. What the single photon interference experiment reveals is that light is neither a classical wave nor a classical particle. It is something for which everyday language has no ready-made category. It produces individual, discrete, localized detection events, which is particle-like. And the statistical distribution of those individual events follows wave interference mathematics, which is wave-like. The two behaviors are not alternatives that light chooses between depending on the experiment. They are both real, observable aspects of the same phenomenon, appearing simultaneously in the same data. Calling it a wave is incomplete because waves don't arrive as discrete clicks. Calling it a particle is incomplete because particles don't produce interference patterns. Saying it's both a wave and a particle sounds accommodating, but it is ultimately unsatisfying, because a classical wave and a classical particle are contradictory things. They cannot literally coexist in the same entity. The phrase wave-particle duality is a convenient label, but it names the mystery rather than solving it. Both pictures, the wave and the particle, were capturing genuine aspects of light's behavior. Neither was wrong about what it described, but each was incomplete, a partial shadow of a deeper reality that neither classical concept could fully represent. The wave picture nailed the interference and diffraction, but missed the discrete energy exchange. The particle picture nailed the individual detection events and momentum transfer, but missed the interference and the frequency dependence. Together they sketched the outline of something that was clearly real, but resisted being squeezed into either classical shape. What light actually is, the deeper truth hiding behind the two incomplete pictures, requires a framework that didn't exist when Einstein proposed his light quanta. It requires a framework that took decades of theoretical development to build, and that fundamentally transformed our understanding of what physical reality is at its most basic level. That framework does not stitch the wave and particle pictures together side by side. It replaces both of them with something more fundamental, something that explains why light looks like a wave when measured one way and looks like a particle when measured another way, without ever actually being either one in the classical sense. And that deeper reality is where we are headed next. So we have two pictures of light, each supported by overwhelming experimental evidence, and each flatly contradicting the other. The wave picture handles interference and diffraction beautifully, but cannot account for discrete energy exchange. The particle picture handles photon detection and momentum transfer perfectly, but cannot explain interference patterns. Saying light is both a wave and a particle names the problem, but it doesn't solve it. What we need is not a compromise between the two classical pictures. We need something deeper, a framework that explains why both sets of observations exist without requiring light to literally be either a classical wave or a classical particle. That framework is quantum field theory, and to understand it, we need to start with the concept at its foundation, the field itself. A field, in physics, is a quantity that has a value at every point in space and at every moment in time. You already have intuitive experience with fields, even if you don't use the word. Temperature is a field. At every point in a room, right now, there is a definite temperature. Near the heater, the temperature is higher. Near the window in winter, it's lower. You can describe the entire room by specifying the temperature at every single point. That collection of values, one temperature for every location, is a temperature field. It isn't a thing you can pick up or throw. It's a condition that exists everywhere throughout a region of space, varying from point to point, changing over time. Wind velocity is another field. At every point in the atmosphere, there is a wind speed and a wind direction. These values change from place to place and from moment to moment. Near the ground, wind might be calm. A few hundred meters up, it might be gusting. The wind field fills the entire atmosphere, assigning a velocity to every point. Now, these everyday examples are useful analogies, but they are not fundamental fields. Temperature is really a summary of the average kinetic energy of jiggling molecules. Wind is really the collective motion of air molecules. These fields are descriptions of underlying particle behavior. They are emergent, derived, approximate. The electromagnetic field is different. It is not a summary of something else. It is not made of smaller parts. According to our best understanding of physics, the electromagnetic field is a fundamental entity in its own right. It exists everywhere in the universe, filling every cubic centimetre of space, including the vacuum of deep space where there is no matter at all. It has a value at every point and at every instant. At each location, the field has an electric component and a magnetic component, and these components can oscillate, strengthen, weaken, and change direction. The field is not a substance floating in space. It is a property of space itself. Space without an electromagnetic field is like a number line without numbers. It's an abstraction that doesn't correspond to physical reality. We've already seen how Maxwell unified electricity, magnetism, and light by showing that the electromagnetic field produces self-propagating waves. But here is the part of that story that matters most for resolving our puzzle, the part that often gets overlooked. Maxwell didn't just discover that electromagnetic waves exist. He revealed that the field itself is physically real. It is not a bookkeeping device, not a convenient shorthand for describing forces between charges. The electromagnetic field carries energy. It carries momentum. It can exist and propagate through regions of space where there is no matter at all. The field doesn't need charges or magnets to justify its existence. It is a fundamental entity in its own right, as real as any material object. So far, this is all classical physics. The electromagnetic field is a smooth, continuous entity that obeys Maxwell's equations. Waves in this field can have any amplitude, any wavelength, any energy. You can make the field oscillate as gently or as violently as you like, with no restrictions. This is the classical wave picture of light, and as we've established, it works magnificently for explaining interference, diffraction, and propagation. But it fails when you examine how the field exchanges energy with matter at the smallest scales. Quantum field theory is what you get when you apply the principles of quantum mechanics to this field, and the result is something profoundly different from either the classical wave or the classical particle. In quantum mechanics, physical quantities that appear continuous in classical physics turn out to be quantized, restricted to specific, discrete values. Energy levels in atoms are quantized. An electron in a hydrogen atom cannot orbit at just any radius with just any energy. It can only occupy specific energy levels. Angular momentum is quantized. Electric charge is quantized. Wherever quantum mechanics touches a physical system, discreteness emerges from what classical physics assumed was smooth and continuous. When you apply quantum mechanics to the electromagnetic field, the same thing happens. The field's energy becomes quantized. The electromagnetic field can carry energy, but not in arbitrary amounts. The energy in any given mode of oscillation of the field, any given frequency and direction of vibration, can only take values that are whole number multiples of a minimum unit. That minimum unit of energy is Planck's constant times the frequency of that mode. This is exactly the quantization that Planck introduced in 1900 and that Einstein used to explain the photoelectric effect. But now we see where it comes from. It comes from applying quantum mechanics to the field itself. And here is the crucial insight. A photon is what we call a single quantum of excitation of the electromagnetic field. It is not a tiny ball sitting inside a wave. It is not a miniature projectile riding along an electromagnetic undulation. It is the field itself, vibrating with exactly one unit of energy in a particular mode. The photon is the field, not something separate from the field, not something the field produces or carries. The photon is a specific quantum state of the electromagnetic field, the state where one particular mode of oscillation contains exactly one quantum of energy. This is a subtle but revolutionary idea, and it resolves the wave-particle puzzle at its root. Think of it this way. Imagine a perfectly still guitar string. The string is there, stretched between two posts, but it isn't vibrating. It's in its ground state, its lowest energy configuration. Now pluck the string. It vibrates, producing a note. The vibration has a specific frequency, a specific wavelength, a specific energy. The vibration isn't a thing separate from the string. It is the string in an excited state. You can't take the vibration off the string and put it in a box. The vibration has no independent existence apart from the string. It is a state of the string. Now imagine the guitar string obeys quantum mechanics. In classical physics, you can pluck the string as gently as you like, giving it any amount of energy. But in the quantum version, the string can only vibrate with specific discrete energy levels. The smallest possible vibration, the gentlest possible excitation, is one quantum. You cannot pluck the string more gently than this. Below one quantum, the string is still. At exactly one quantum, the string vibrates at its minimum possible amplitude. 2 quanta means a larger vibration. 3 quanta means larger still, but you cannot have 1.5 quanta. The energy comes in whole units. The electromagnetic field is like this quantum guitar string, but vastly more complex. Instead of a single string with one fundamental frequency, the electromagnetic field has modes of oscillation at every possible frequency, in every possible direction, at every point in the universe. Each mode can be excited by discrete amounts. 1 quantum of excitation in a mode with a frequency corresponding to red light is a red photon. 1 quantum in a mode with a frequency corresponding to blue light is a blue photon. 1 quantum in a mode with a frequency corresponding to gamma rays is a gamma ray photon. The photon is not a separate thing from the field. The photon is the field, carrying 1 unit of excitation in one particular mode. This picture immediately explains why the photon has properties of both waves and particles without being either one in the classical sense. The wave-like properties come from the field. The electromagnetic field is a continuous entity that fills all of space. It has wavelength, frequency, phase, and all the other properties that waves have. It can interfere with itself. It can diffract around obstacles. These are properties of the field's oscillation modes, the shapes and frequencies of the ways the field can vibrate. When you see an interference pattern, you are seeing the structure of the field's modes. The field naturally produces interference because its oscillation modes have phase relationships that add constructively at some locations and destructively at others. This is simply what oscillating fields do. No mystery there. The wave behavior is a property of the underlying field. The particle-like properties come from the quantization. The field's energy comes in discrete packages. You cannot have half a quantum. When the field interacts with matter, it does so one quantum at a time. When a photon is absorbed by an atom, the field loses exactly one quantum of energy in that mode, and the atom gains exactly that amount. When a photon is detected by a photodetector, one quantum is removed from the field, producing a single click. The discreteness, the all-or-nothing character of detection events, the individual dots on a detector screen, all of this comes from the quantization of the field's energy. This is inherently particle-like behavior, not because tiny balls are flying through space, but because the field's energy is grainy. It comes in lumps. You cannot smoothly drain the field of energy. You can only remove whole quanta, one at a time. So the wave behavior and the particle behavior are not two competing descriptions of the same thing. They are two different aspects of the same thing. Two different faces of the quantum electromagnetic field, revealed by different kinds of measurements. This is the answer to the puzzle. Light is not a wave. Light is not a particle. Light is a quantum field excitation that has some measurable properties that resemble classical waves and other measurable properties that resemble classical particles, without actually being either one. Here is another way to see it. Think about what happens when you perform different types of experiments on light. The experiment you choose determines which aspect of the quantum field you observe. This is not because the field changes depending on the experiment. The field is always the same underlying entity, but different experiments are sensitive to different properties. An interferometer, for example, is designed to detect phase relationships. You split a light beam into two paths and recombine them. The resulting pattern depends on the difference in the distances traveled along the two paths, because that difference determines how the oscillation phases of the field along those two paths line up when they reunite. If the phases align, crest meeting crest, you see constructive interference, a bright spot. If they are opposite, crest meeting trough, you see destructive interference, a dark spot. The interferometer is probing the field's phase structure, and phase structure is a wave-like property. So the interferometer reveals wave-like behavior. It shows you the spatial structure of the field's oscillation. A photodetector, by contrast, is designed to absorb individual quanta. When a quantum of the field is absorbed by an electron in the detector material, the electron is ejected or excited, and a signal is produced. The detector doesn't care about phase. It doesn't measure wavelength directly. It registers the arrival of one quantum of energy. The detector reveals particle-like behavior. It shows you the granularity of the field's energy. Both experiments are examining the same physical entity, the quantum electromagnetic field, but they are extracting different information from it. The interferometer asks about phase structure and gets a wave-like answer. The photodetector asks about energy delivery and gets a particle-like answer. The field doesn't switch between being a wave and being a particle. It doesn't know or care what experiment you're performing. It simply is what it is, a quantum field. And different measurements access different aspects of that one, unchanging reality. This brings up something important. The word measurement can be misleading. It sounds like it requires a person doing the measuring, someone watching, deciding, paying attention. But measurement in quantum mechanics is not a mental act. It is a physical interaction. When a photon is absorbed by a detector, that absorption is a physical event involving the quantum field and the atoms in the detector material. It happens whether or not any human is present, and it would happen exactly the same way on an uninhabited planet orbiting a distant star. What determines the result is the physical configuration of the apparatus, the type of interaction that takes place, not anyone's awareness or attention. What the measuring apparatus does is select which property of the quantum field gets recorded. An interferometer records phase correlations. A photodetector records energy quanta. Both properties exist simultaneously in the field, but no single experiment can reveal both fully and simultaneously. This is deeply connected to the Heisenberg uncertainty principle, which says that certain pairs of physical properties cannot both be precisely determined at the same time. Knowing the precise phase of the field is incompatible with knowing the exact number of quanta. Experiments that reveal one suppress the other. This is not a technological limitation, it is a fundamental feature of quantum mechanics. The field possesses both kinds of properties, but the properties are complementary in the precise quantum mechanical sense, meaning they cannot both be sharply defined at the same instant. There is another important point to make clearly. The electromagnetic wave and the photon are not two separate entities that coexist side by side. This is a common misunderstanding. People sometimes imagine a classical electromagnetic wave rippling through space like an ocean swell, with tiny photon particles embedded in it like surfers riding the crests. That picture is wrong. There is not a wave with particles in it. There is one thing, the quantum electromagnetic field, and that one thing produces wave-like measurement results in some experiments and particle-like measurement results in others. The wave and the photon are two incomplete descriptions of the same single entity. They are not two ingredients mixed together. Here is an analogy that might help, imperfect as all analogies must be when describing quantum phenomena. Imagine you have a friend you've never met in person. You've only spoken to them by phone and exchanged letters. Over the phone, their personality seems one way: spontaneous, energetic, responsive. In letters, their personality seems different: thoughtful, measured, precise. You might wonder whether your friend has two personalities, but when you finally meet them in person, you discover they are one person with a rich, complex character that expresses itself differently through different channels of communication. The phone captured some aspects, the letters captured others. Neither was wrong, neither was complete. Your friend didn't switch personalities depending on the medium. They were always the same person, and the different impressions came from the different ways you interacted with them. Light is similar. The wave picture captures what you learn through interference experiments. The particle picture captures what you learn through detection experiments. Neither picture is wrong, neither picture is complete. And light doesn't switch between the two. It is always the same quantum field excitation, expressing different measurable aspects through different types of experimental interaction. The framework that makes all of this precise and mathematically rigorous is called quantum electrodynamics, often abbreviated as QED. This theory was developed through the 1920s, 30s, and 40s by physicists including Paul Dirac, Werner Heisenberg, Wolfgang Pauli, Pascual Jordan, and later brought to its most complete form by Richard Feynman and others in the late 1940s. Quantum electrodynamics is the quantum field theory of the electromagnetic field and its interaction with charged particles like electrons. In quantum electrodynamics, photons and electrons are both treated as excitations of their respective quantum fields. The electromagnetic field gives rise to photons. The electron field gives rise to electrons. These fields interact. An electron can absorb a photon, which means the electron field gains energy, while the electromagnetic field loses one quantum. An electron can emit a photon, which means the electron field loses energy, while the electromagnetic field gains 1 quantum. Every interaction between light and matter is described as an exchange of quanta between fields. The predictions of quantum electrodynamics have been tested to extraordinary precision. One of the most precisely measured quantities in all of physics is the magnetic moment of the electron. Quantum electrodynamics predicts this quantity to more than 10 decimal places. The experimental measurement agrees with the prediction to more than 10 decimal places. This level of agreement is staggering. It's like predicting the distance from London to New York to within the thickness of a human hair. No other theory in the history of science has been confirmed to this degree of accuracy. Quantum electrodynamics also explains phenomena that neither the classical wave picture nor the simple photon picture could account for. It explains the Lamb shift, a tiny splitting of energy levels in hydrogen that the best earlier quantum equations predicted should be identical, but are not. It explains the Casimir effect, a measurable attractive force between 2 uncharged metal plates in a vacuum, caused by quantum fluctuations of the electromagnetic field. It explains how light scatters off light, a process where 2 photons interact indirectly through the quantum fields of virtual electron-positron pairs, something that would be impossible if photons were just classical waves or classical particles passing through each other without interaction. So, quantum field theory does more than resolve the wave-particle puzzle. It provides a deeper and more powerful description of electromagnetic phenomena than either classical picture could achieve alone. The wave picture and the particle picture weren't wrong. They were limited. They were low-resolution glimpses of a higher-resolution reality. Quantum field theory is that higher-resolution picture. But let's be honest about what this means and what it doesn't mean. Quantum field theory tells us that light is a quantized excitation of the electromagnetic field. This is the best answer physics currently has for what light actually is. But it doesn't make the strangeness go away entirely. The quantum field still behaves in ways that defy everyday intuition. The field is still spread out through space like a wave. Its excitations are still discrete like particles. A single photon still passes through both slits and interferes with itself. Individual detection events are still localized and random, with their probabilities governed by the field's wave-like structure. The mathematics of quantum field theory handles all of this consistently and makes predictions that match experiments with breathtaking accuracy. But the picture it paints is one that no classical analogy fully captures. This is perhaps the most important lesson. Nature is not obligated to resemble anything we encounter in everyday life. Our intuitions about waves come from watching oceans and guitar strings. Our intuitions about particles come from throwing baseballs and watching billiard balls collide. These are macroscopic classical systems, containing trillions upon trillions of quanta. Systems where quantum effects average out and classical behavior emerges. At the quantum level, where individual excitations of fields are involved, nature behaves differently. Not inconsistently, not illogically, just differently from the large-scale phenomena our brains evolved to understand. The quantum electromagnetic field is real. It has been measured, probed, tested, and confirmed across a century of experiments, with precision unmatched in any other domain of science. It is the thing that light actually is. Not a classical wave that somehow also produces clicks in detectors. Not a classical particle that somehow also creates interference fringes. It is a quantum entity, an excitation of a fundamental field that fills the universe, and its behavior is described not by classical wave equations or classical particle mechanics, but by the mathematics of quantum field theory. The phrase wave-particle duality is fine as conversational shorthand. It communicates the key experimental facts quickly. Light shows wave behavior and particle behavior depending on how you measure it. But if you take the phrase literally, if you imagine that light is genuinely a classical wave and simultaneously a classical particle, you will be confused, because those two things are logically incompatible. The resolution is not that light somehow manages to be two contradictory things at once. The resolution is that light is neither of those things. It is a third kind of entity, a quantum field excitation that was unknown before the 20th century and that doesn't have a name in everyday language. We borrowed the words wave and particle from everyday experience because they were the closest things we had. But they are approximations, shadows on the wall of a cave, hinting at a shape we couldn't fully see until quantum field theory illuminated it. When Maxwell unified electricity, magnetism, and light in the 1860s, it was one of the great triumphs of classical physics. When Einstein showed in 1905 that light carries energy in discrete quanta, it was the beginning of quantum physics. When Dirac, Feynman, and their colleagues constructed quantum electrodynamics in the middle of the 20th century, they achieved something even greater. They showed what the electromagnetic field really is at the deepest level we currently understand. Not a classical wave, not a stream of classical particles, but a quantum field whose excitations carry discrete energy and momentum, while simultaneously possessing the phase structure and spatial extent of waves. This is what light is. Not a wave pretending to be a particle, not a particle pretending to be a wave. Not an indecisive entity switching between two identities. Light is a quantum excitation of the electromagnetic field, an entity with no analogue in our everyday experience, an entity that does what it does regardless of what classical label we try to pin on it. The wave and the particle were always just metaphors. Good metaphors, useful metaphors, metaphors that captured real and important aspects of the truth, but metaphors nonetheless. The reality they were reaching for is the quantum field, and the quantum field is neither a classical picture. It is something entirely its own. Everything we've discussed so far has been about light, but here is what makes this story truly extraordinary. Light is not special. The same logic, the same resolution, the same quantum field picture applies to everything in the universe. Every particle you have ever heard of, every building block of every atom in every object you have ever touched, is the same kind of entity as the photon. Not a classical wave, not a classical particle, a quantum excitation of an underlying field. This realization didn't come from studying light alone. It came from studying matter, and particularly from studying the electron. In 1924, a French physics student named Louis de Broglie proposed something that sounded almost reckless. If light, which everyone assumed was a wave, turned out to have particle-like properties, then perhaps matter, which everyone assumed was made of particles, might have wave-like properties. De Broglie suggested that every particle with momentum should have an associated wavelength. The relationship is simple and elegant. The wavelength equals Planck's constant divided by the particle's momentum. Higher momentum means shorter wavelength. Lower momentum means longer wavelength. For everyday objects, the wavelength is absurdly small. A baseball pitched at 40 meters per second has a de Broglie wavelength of roughly 10 to the negative 34 meters, a distance so small it approaches the Planck length, completely unmeasurable by any conceivable instrument. The wave nature of a baseball is real in principle, but it has no observable effect. The baseball behaves entirely like a classical particle, because its wavelength is incomprehensibly smaller than any object it encounters. But electrons are different. Electrons have very small mass, roughly 9 times 10 to the negative 31 kilograms. When electrons are accelerated through modest voltages, their de Broglie wavelengths become comparable to the spacing between atoms in a crystal, roughly a fraction of a nanometer. At this scale, wave effects should be detectable. And in 1927, just 3 years after de Broglie's proposal, they were. Clinton Davison and Lester Germer, working at Bell Labs in the United States, fired a beam of electrons at a nickel crystal and observed the reflected electrons. If electrons were classical particles, they should scatter in all directions, with perhaps some preference for the angle of reflection. But Davison and Germer found something startlingly different. The electrons reflected preferentially at very specific angles, creating a pattern of strong and weak signals. This pattern was an unmistakable diffraction pattern, identical in structure to the patterns produced when X-rays, which are electromagnetic waves, diffract off crystal lattices. The electrons were diffracting. They were exhibiting wave behavior, and the angles matched precisely what de Broglie's wavelength formula predicted. Independently, in Scotland, George Paget Thomson performed a similar experiment, firing electrons through thin metal foils and observing concentric rings of diffraction on a photographic plate behind the foil. The pattern was exactly what you would expect from waves passing through a regular array of atoms and interfering constructively at certain angles and destructively at others. Thomson's rings matched the predictions of wave theory with impressive precision. The evidence was decisive. Electrons, which were known to be particles with definite charge and definite mass, entities that could be individually counted and deflected by electric and magnetic fields, also exhibited interference and diffraction. The same two signatures of wave behavior that had proven light was a wave in the 1800s now prove that electrons, quintessential particles of matter, also behave as waves. And then came the most dramatic demonstration of all. Physicists performed the double-slit experiment with electrons, one electron at a time, exactly as had been done with photons. An electron gun fires individual electrons toward a barrier with 2 narrow slits. Behind the barrier sits a detector screen. The source is dimmed until only 1 electron passes through the apparatus at a time. There is never more than a single electron between the gun and the screen. Each electron arrives at the screen and registers as a single point, a tiny dot at a specific location. Early on, with just a few dozen electrons recorded, the dots appear randomly scattered, as if each electron simply picked a spot at random. But as hundreds, then thousands, then tens of thousands of electrons accumulate, the dots organize themselves into alternating bands of dense and sparse regions. An interference pattern emerges, identical in structure to the pattern produced by light in Thomas Young's experiment over 2 centuries earlier. Individual electrons, fired one at a time through 2 slits with nothing else present to interfere with, collectively build a wave interference pattern on the detector screen. Each electron arrives as a discrete particle. The cumulative pattern follows wave mathematics. The electron is neither a classical particle nor a classical wave. It is the same kind of entity as the photon, a quantum excitation of an underlying field, in this case, the electron field. And this is not unique to electrons. The same behavior has been demonstrated with neutrons, with atoms, with molecules containing dozens or even hundreds of atoms. In the year 2019, researchers in Vienna performed an interference experiment with molecules containing nearly 2,000 atoms each, enormous by quantum standards, and still observed wave-like interference. Every material object tested, from the smallest subatomic particle to complex molecules, exhibits the same quantum behavior. Individual, discrete detection events whose statistical distribution follows wave interference mathematics. The duality is universal. It is not a quirk of light. It is a feature of everything. This universality is precisely what quantum field theory describes. In this framework, every type of fundamental particle corresponds to its own quantum field pervading all of space. The electromagnetic field gives rise to photons. The electron field gives rise to electrons. The quark fields give rise to quarks, which combine to build protons and neutrons. The neutrino fields give rise to neutrinos. The Higgs field, whose existence was confirmed in 2012 at the Large Hadron Collider, gives rise to the Higgs boson and plays a role in giving mass to other particles. Each field fills the entire universe, existing at every point in space and at every moment in time. Each field can be excited, and a single quantum of excitation of a particular field is what we call a particle of that type. An electron is not a tiny ball orbiting an atomic nucleus. It is a quantum of excitation of the electron field. A quark is not a hard little pellet jammed inside a proton. It is a quantum of excitation of the quark field. Every particle in the Standard Model of Physics, the comprehensive catalogue of all known fundamental particles and forces, is understood this way. The particles are not separate from the fields. They are the fields in excited states. This means the universe at its most fundamental level is not made of things, it is made of fields. Space is not an empty container in which particles happen to exist. Space is filled with quantum fields, layered on top of one another, permeating every point. What we perceive as matter, as substance, as solid, tangible stuff, is really the result of quantum fields vibrating in specific patterns. The chair you sit on, the air you breathe, the body you live in, all of it is quantum field excitations interacting with one another according to the rules of quantum field theory. The solidity you feel when you touch a table is not tiny billiard balls stacking up against each other. It is quantum fields repelling each other through electromagnetic interactions at atomic scales. This picture is not speculation. It is the foundation of the Standard Model of particle physics, the most thoroughly tested and precisely confirmed theory in the history of science. Every prediction the Standard Model has made, and it has made thousands, has been confirmed by experiment. The existence of the Higgs boson was predicted decades before it was detected. Particle masses, decay rates, scattering angles, and energy levels are all calculated from quantum field theory, and every measurement matches the predictions. The theory has been tested thousands of times across decades of experiments, and it has never been wrong. Now, armed with this understanding, let's revisit some of the misconceptions that cloud public understanding of light and quantum physics. The first and most common misconception is that light switches between being a wave and being a particle depending on the experiment. You hear this phrasing constantly. In this experiment, light is a wave. In that experiment, light is a particle. It decided to be a wave this time. It chose to be a particle that time. This language implies that light has two distinct modes of existence and toggles between them based on external circumstances. That is not what happens. Light is always the same thing, a quantum excitation of the electromagnetic field. It does not change its nature. It does not flip a switch. Different experiments measure different properties of the same unchanging entity. An interferometer measures phase structure. A detector measures energy quanta. Both properties coexist in the quantum field at all times. The experiment does not cause the field to transform into one thing or another. The experiment selects which property gets recorded. The field itself remains the same before, during, and after the measurement. The second misconception is that the observer consciously creates reality. This idea has leaked from quantum physics into popular culture, self-help books, and films. The basic claim is that human consciousness is somehow necessary to collapse the quantum wave function, that reality is undefined until a conscious mind looks at it, and that you can influence physical outcomes by thinking about them in the right way. This is not what quantum mechanics says. Measurement in quantum mechanics is a physical interaction between the quantum system and the measuring apparatus. It doesn't require a conscious observer. A Geiger counter clicks when a radioactive atom decays, whether or not anyone is listening. A photographic plate records photon impacts whether or not anyone develops the film. A satellite detector registers gamma-ray photons in deep space, whether or not any human ever downloads the data. Consciousness plays no special role in quantum mechanics. The measurement problem, the question of how definite outcomes arise from quantum superpositions, is a real and unsolved puzzle in the foundations of physics. But none of the leading interpretations require consciousness to play any part. The physical apparatus does the work. The human mind is a spectator. The third misconception is that the double-slit experiment proves that light or electrons literally travel through both slits simultaneously and then somehow recombine. This is a tempting interpretation, and it captures something real, but it imposes classical thinking where classical thinking doesn't apply. In the quantum field picture, the field excitation evolves according to quantum mechanical rules. It doesn't have a classical trajectory. It doesn't travel through one slit or the other in the way a marble would. And saying it travels through both simultaneously is still forcing a classical particle concept, the idea of a localized thing following a path, onto an entity that simply doesn't work that way. The quantum field excitation has a certain mathematical structure, described by its quantum state, and that state evolves to produce probabilities for detection at various locations on the screen. Some locations have high probability, others have near zero probability. The alternating pattern of high and low probabilities is the interference pattern. This is what the mathematics describes. The field excitation doesn't need to travel through both slits for this to work. The concept of traveling through a slit is a classical idea being misapplied. The quantum state of the field takes both paths into account in its evolution, without anything actually needing to be in two places at once, in any classical sense. The fourth misconception is that wave-particle duality is the final word, the deepest description physics has to offer. It is not. Wave-particle duality is a historical stepping stone. It is the observation that launched the development of quantum mechanics. But quantum field theory goes beyond duality. It replaces the two incomplete classical pictures with a single, coherent, unified description. Calling something a quantum field excitation is not just a fancier way of saying it's both a wave and a particle. It is a genuinely different and deeper description. A quantum field excitation has properties that neither classical waves nor classical particles possess. It has quantized energy exchange, which is particle-like. It has phase coherence and spatial extent, which is wave-like. But it also has properties that are uniquely quantum, like entanglement, superposition, and the specific probability structures that govern measurement outcomes. These have no analogues in classical waves or particles. Wave-particle duality was a signpost pointing toward the truth. Quantum field theory is the truth it was pointing toward. So what does all of this tell us about the nature of physical reality? It tells us something that is simultaneously humbling and awe-inspiring. The universe is not made of solid objects. At its most fundamental level, the universe is made of fields. Quantum fields fill every point in space. They vibrate, fluctuate, interact, and exchange quanta of energy and momentum. What we call particles are the discrete excitations of these fields. What we call forces are interactions between fields. What we call matter is a particular arrangement of field excitations interacting through other fields. The air in the room where you are sitting right now is made of nitrogen and oxygen molecules. Each molecule is made of atoms. Each atom has a nucleus surrounded by electrons. The nucleus is made of protons and neutrons. Each proton and each neutron is made of 3 quarks bound together by gluons. Every one of these entities, the electrons, the quarks, the gluons, is a quantum excitation of its corresponding field. And the forces holding them together, the electromagnetic force keeping electrons bound to nuclei, the strong nuclear force holding quarks inside protons, are mediated by the exchange of quanta of other fields. Photon exchange mediates the electromagnetic force. Gluon exchange mediates the strong force. The entire structure of matter, from the largest molecule down to the smallest quark, is fields interacting with fields. You are made of quantum field excitations. The atoms in your body, the oxygen in your lungs, the calcium in your bones, the iron in your blood, every last component is an excitation of a quantum field. You are not a collection of tiny solid balls held together by little sticks, despite what ball and stick chemistry models might suggest. You are a fantastically complex, dynamically stable pattern of interacting quantum field excitations. The fields were here before you were born. They will be here after you die. You are a temporary configuration, a ripple in the quantum fields, a transient arrangement of excitations that persists for a few decades and then dissolves, the energy and matter cycling back into the fields from which they came. The light entering your eyes right now is the electromagnetic field oscillating. The nerve impulses traveling from your retina to your brain are disturbances in the electron field propagating along neurons. The chemical bonds holding your DNA together are electromagnetic field interactions between electron field excitations. At every level, from the largest to the smallest, the description is the same. Fields, quanta, interactions. This is not a metaphor. It is not poetry dressed up as physics. It is the literal content of our best and most precisely confirmed physical theory. Quantum field theory is the mathematical framework underlying the standard model of particle physics, and every experiment performed over the past 8 decades is consistent with its predictions. And it all started with the simple question we asked at the very beginning: what is light? The answer turned out to be far stranger and far more wonderful than anyone expected. Light is not a wave. Light is not a particle. Light is a quantum excitation of the electromagnetic field, an entity with no classical analogue, an entity that forced physicists to rebuild their entire understanding of nature from the ground up. The discovery that light is a quantum field excitation didn't just solve the puzzle of wave-particle duality. It opened the door to the entire modern understanding of the physical world. It led to quantum electrodynamics, the most precise theory ever constructed. It led to the Standard Model, which catalogues every known fundamental particle and force. It led to the understanding that all of reality is built from quantum fields. Every step of that intellectual journey began with people looking carefully at light and refusing to accept an answer that didn't fully explain what they observed. Thomas Young saw interference fringes and proved light has wave properties. Einstein saw the photoelectric effect and proved light has particle properties. Dirac and Feynman built quantum electrodynamics and showed what light actually is. Each generation asked the question more precisely and accepted the answer more honestly, even when the answer was strange, even when it contradicted common sense, even when it required abandoning deeply held assumptions about the nature of reality. That willingness to follow evidence wherever it leads, even into territory that makes no intuitive sense, is the heart of physics. Nature does not care about our comfort. It does not organize itself to be easily understood by beings who evolved to track predators on the savannah and find ripe fruit in the trees. Nature is what it is, and the fact that it turns out to be built from quantum fields rather than from tiny balls or smooth waves is nature's business, not ours. Our business is to observe, to measure, to calculate, and to accept what the evidence says, even when what it says is deeply, irreducibly strange. There is a tendency in popular science to present quantum mechanics as mystical, as a doorway into a reality where anything is possible, where observation creates existence, where the universe is whatever you want it to be. That framing does a disservice to one of humanity's greatest intellectual achievements. Quantum mechanics is not mystical. It is precise. It is mathematical. It makes specific, testable predictions that have been confirmed to extraordinary accuracy. It does not say anything goes. It says very specific things go and other things don't. and the mathematics tells you exactly which is which. What quantum mechanics does say is genuinely strange. The universe is made of fields, not solid objects. These fields have quantized excitations that behave unlike anything in everyday experience. Measurement reveals specific properties, while necessarily leaving others uncertain. Individual quantum events are genuinely random in a way that no hidden variable can explain. Distant quantum systems can be entangled in ways that defy classical explanation. These things are strange, but strange is not the same as mystical. Strange is the universe being honest with us about its own structure, even though that structure turns out to be nothing like what we naively expected. Light taught us all of this. A beam of sunlight warming your face on a summer afternoon is the electromagnetic field oscillating, its quanta streaming from the sun across 150 million kilometers of empty space, each photon carrying a precise amount of energy determined by its frequency, each one a quantum excitation of the field that fills the universe. Those photons were created in the nuclear furnace at the sun's core, where hydrogen nuclei fuse into helium, releasing energy that excites the electromagnetic field into new photon states. They bounced around inside the sun for over 100,000 years, absorbed and re-emitted countless times, gradually working their way outward until they finally escaped from the solar surface. Then they travelled through 8 minutes and 20 seconds of empty space, crossed the vacuum at 300,000 kilometers per second, entered Earth's atmosphere, passed through the air, and landed on your skin. Each one delivered one quantum of energy to the molecules in your skin cells, warming you. Every step of that journey, from nuclear fusion to warmth on your face, is described by quantum field theory. The fusion reactions in the sun's core are interactions between quark fields and the fields that mediate the weak and strong nuclear forces. The photons created in those reactions are excitations of the electromagnetic field. The propagation of light through space is the evolution of those field excitations according to Maxwell's equations, which are themselves the classical limit of quantum electrodynamics. The absorption of light by molecules in your skin is the transfer of quanta from the electromagnetic field to the electron fields in those molecules. Fields, quanta, interactions, all the way through. One coherent, unified picture from the heart of a star to the surface of your hand. The question we started with tonight seemed simple. Is light a wave or a particle? The answer turned out to require rethinking the foundations of physics. Light is neither a classical wave nor a classical particle. It is a quantum excitation of the electromagnetic field, an entity that has wave-like and particle-like measurable properties without being either one. The same is true of electrons, of quarks, of every fundamental constituent of matter. The universe is made of quantum fields, and particles are how those fields express their energy. This is one of the deepest truths physics has uncovered. It is supported by a century of experiments of extraordinary precision. It is the foundation of our most successful physical theories, and it began with something as simple and as familiar as a beam of light. The next time you see sunlight streaming through a window, casting patterns of brightness and shadow across a room, remember what you now know. That light is not a wave rippling through space like water on a pond. It is not a spray of tiny bullets fired from the sun. It is the quantum electromagnetic field, vibrating in quantized excitations, each one carrying a precise packet of energy and momentum, each one exhibiting the phase structure and spatial extent of waves, while delivering energy in the discrete, indivisible portions of particles. It is something for which everyday language has no perfect word, something that existed long before humans evolved to wonder about it, something that taught us, when we finally looked closely enough, that reality at its deepest level is stranger, more subtle, and more beautiful than anything we ever imagined. And that is what light is.